Perfect. Okay. Thanks, Rolando. All right. So today we're going to do, well, I guess I should introduce myself. So I'm Maggie Reardon. I am a sixth-year PhD student at CU Boulder, and I work under Robin Deely. So what we're going to do today is finish up what Rachel was talking about yesterday. So we're going to talk some more about some properties of K-theory, and then we're going to spend the rest of the time discussing some examples of computing K-theory for C-star algebras that are more tangible, but more complicated than the ones that we saw yesterday. Okay, so let's recall what we did yesterday. So if A is a unital C-star algebra, I promise we will talk about the non-unital case today as well. We defined the K0 group of our C-star algebra A to be the growth and decompletion of all of the projections in the matrix amplifications of our C-star algebra A modulo that equivalence relation that Rachel discussed last time. And this is an abelian group. The way that we add our K0 classes in here is by doing our direct sum, which that sends it to a matrix with P and Q on our diagonal. Okay, so last time, Rachel computed a couple of the K0 groups for certain C-star algebras just by definition. So she did the complex numbers. She also did n by n matrices with complex entries. And she also did the compact operators. And we found that the K0 groups of all of these will be the integers. So we are going to discuss a different method today of computing this as well, because I don't think we did as much detail on that computation. And we also found that the K0 group of the bounded operators is 0. Okay, so let's focus on K0 for right now. And let's talk about some more properties that we can have with K0. So also, I didn't mention this, but if you have any questions while I'm going, go ahead and either put it in the chat or unmute yourself and ask. I'm more than happy to be interrupted. So we have this notion of maps between C-star algebras. It's a star homomorphism. So we would hope that that would give us a map on K-theory, and it does. So let's say that we have a star homomorphism. I'm going to call it phi between, let's say we have unital C-star algebras for right now, and we'll call them A and B. And then we can define the induced map on their K0 groups. And we call this induced map K0 of phi. You might see it being referenced as just a phi 0 or sometimes just a phi star. I will try to be very careful with my notation and keep it as K0 of phi, but you'll see this in other resources as well. So this is a group.
Right. Can I actually ask a clarification question?
Yeah, of course.
So above we said that K0 of the n by n matrices complex entries is Z, but
Mhm.
K0 of B of H is 0. So is that if H is infinite dimensional?
Yes, yeah. So we're looking at infinite dimensional separable Hilbert spaces, just that.
Yeah, thanks.
Yeah, good
Since
question.
I guess matrices would be for the finite dimensional case of Hilbert space.
Yes, I believe so. I don't know. I don't really do a lot of not or finite dimensional Hilbert spaces, but yes, all whenever I'm talking about like compact operators or bounded operators, that's on the separable infinite dimensional Hilbert space.
Yeah, that's right. If it's finite dimensional, you can write it as a decomposition of matrices. So yeah, it's reasonable to assume here that H is infinite dimensional.
Yeah. And we'll talk about finite dimensional C-star algebras later as well. So okay, cool. Yeah, so we've got this induced map on our K0 groups. You can show that this will be a group homomorphism, but this goes from K0 of A to K0 of B. So it preserves the order, like the direction, I guess. And the way that we define this is we take a class, a K0 class, and we map it to phi of that projection, or one of the projections in our class, and we look at the K0 class of that in B. So this makes a lot of sense if we are considering a projection in A. But the definition isn't so clear if I'm considering a projection in a matrix amplification. So let's see what that will look like. So if I have a projection in, we have notation for this. I don't need to write it all out. If I have a projection in the matrix amplification of A, then what we say here is we define phi of P where P is now a matrix with entries in A. We define this as you just look at the matrix where you apply phi to every entry. Okay, because phi is defined on the C-star algebra A. So that's how we define this map here. And this makes K0 a functor. And this is a functor from the category of C-star algebras into the category of abelian groups. Okay. So there are some nice properties of this functor. One of them being that K0 is half exact. So I guess it's not super nice, but it could be worse. So what that means is if I have a short exact sequence of C-star algebras, A, B, C, then we get that K0 induces, that's not how you spell that. There we go. The exact sequence. Let's give these names. Where we have K0 of A and our induced map here into K0 of B. Our induced map for this and K0 of C. So we don't have that this induces a short exact sequence on K theory. That's what the half exact means here. So there are some examples in Rordom, which I will post the link to that again later, that PDF, that show that we don't get a short exact sequence for the K theory groups in every instance. Okay. But we do have that K0 is split exact. So if I have a split exact sequence, I'll say a little bit about what that is of C-star algebras. So A, B, C. So like we had before, I have a short exact sequence, but now I have a splitting. So I can go back. Okay. So if we have this, then K0 induces a split exact sequence on the level of K theory groups. So now we do have an exact sequence of our K theory groups that splits. Now I'm not going to write all of the induced maps out, but you can imagine what that would look like. Okay. So now that we have these properties, also I'm not proving any of this. Rordom goes through in detail proving these properties. So right now what we're going to do is we're just going to take it for granted and we're going to apply it in some example computations. But if you're interested in seeing why this is the case, I suggest you look at Rordom. And I'll post the link to that PDF. But now we're able to talk about how we define the K0 group of a non-unital C-star algebra. So Rachel kind of mentioned yesterday that we could define the K0 group of a non-unital C-star algebra the same way that we defined it for a unital C-star algebra. The problem here is that the functor would then not be half exact. And that's an issue if you want to define a homology theory. Okay, so we need to alter our definition a little bit to make sure that these properties that we have listed above still hold, because those are really nice when we want to do, any sort of computation. And it's important for us to define what K0 of a non-unital C-star algebra is, because as we know, not every C-star algebra that we work with is unital. Okay. So what we do is we relate this to the unitization of our C-star algebra. So let's say that I have a non-unital C-star algebra A. I can consider its unitization. And we know that we have a split exact sequence involving these C-star algebras. So I can include my non-unital C-star algebra into its unitization, and then I can project down to the complex numbers. That gives me a short exact sequence, but I want this to be a split exact sequence. So I'm going to define a map going from the complex numbers to the unitization. And what that does is it takes a complex number and it sends it to scalar multiplication by the unit in our unital C-star algebra. Okay. So what we do here is we consider the induced split exact sequence for our K0 groups, and we define K0 of our non-unital C-star algebra to be the kernel of the induced map on K0 of that projection, pi, okay? And because we have that K0 is a split exact functor, what we get is that this middle term in K0 will be isomorphic to the direct sum of the K0 groups of the outside terms. And so we have that K0 of our unitization is isomorphic to K0 of our non-unital C-star algebra, direct sum a copy of Z, because that is the K0 group of the complex numbers. So if we know the K-theory of the unitization, we can figure out the K-theory of the non-unital C-star algebra. Okay. Do you have any questions on this before I move on? All right. So I was focusing a lot on K0, but similar properties hold for K1. So K1 is going to be a functor as well from the category of C-star algebras into that of the abelian groups. So maybe let's remember how we defined K1. So K1 of a C-star algebra can be unital, can be non-unital, doesn't really matter. This is isomorphic to the unitaries in all the matrix amplifications of the unitization of our C-star algebra A modulo an equivalence relation. And Rachel also computed the K-theory, or the first K-theory group of a couple of the C-star algebras that we mentioned before, N of C, and then also B of H, and found that these were all trivial. Okay. So these are the, I guess, most basic C-star algebras that we can consider when discussing K-theory. These are the ones that you can compute by the definition of K-theory. The other ones that we are going to consider today, we need some more tools. But the goal of the rest of this talk is to compute K-theory groups for other examples. And we'll also learn more tools as we go. Okay. So let's see. Let's talk about some classes of C-star algebras and some specific examples that we can consider. So the next, in my mind, the next step up from the complex numbers, matrices over the complex numbers, and B of H would be to consider finite dimensional C-star algebras. And I believe you have seen this before. It's in the goals notes that any finite dimensional C-star algebra is isomorphic to a direct sum of square matrices over the complex numbers of varying sizes, potentially. So let me write this out. Where these are just going to be in our natural numbers. This is, I did look it up, proposition 8.5 in the goals notes if we're not sure where this isomorphism is coming from. It's a non-trivial proof and it involves G and S. But it's something that you can check if you need to. So we know the K-theory of each of these terms. We are hoping that K-theory would play nicely with the direct sum, because then we could figure out what the K-theory of this C-star algebra is. And that's actually the case here. It's stated as two different propositions in Rordom. I'll list them out here so you can take a look at the proofs if you're interested. So the first one deals with K0 and the second deals with K1. But again, this is coming from Rordom. But I'm going to state this as for both of them. So A and B, let's just say they're C-star algebras. Then if I want to find the K-theory of the direct sum, this will be isomorphic to the direct sum of their respective K-theory groups, where star can be 0 or 1. Okay? So more specifically, we can say where this isomorphism is coming from. If I consider the inclusion of A into the direct sum of A with B and that of B, then if I look at the induced map on K-theory, oops, A first. This will give me my isomorphism. But let's actually say how this map is defined. So let's say I am looking at this element GH, where G and H represent K0 or K1 classes in our respective C-star algebras, or for our respective C-star algebras. Then what this gets mapped to is I'm going to have, oh, I keep messing that up. I'm going to have the induced map of the inclusion of A act on G, and then likewise for B act on H. I'm just going to add those two together. And this is a group isomorphism for star equals 0 or 1. Okay. So K-theory, this functor respects direct sums in this really nice way. Like we know explicitly what this isomorphism is. So we can apply this now for any arbitrary finite dimensional C-star algebra. So let's say that A is the direct sum of n, oopsies, matrix algebras, where our indices are in the natural numbers. Then we can find its K0 group and its K1 group, but we'll start with K0. So this is isomorphic to taking the K-theory of the direct sum. Rachel discussed that last time, saying that if two C-star algebras are isomorphic, their K-theory groups will be isomorphic. And we can apply that proposition above to say that this will be the direct sum of the K-theory groups of our matrix algebras. Okay, and we know what the K0 group of this is, right? This is just the integers. So I have the integers being summed together n times. Okay, great. What do you think happens for K1? What do you think this will be? No guesses?
It'll be 0, right?
It'll be 0. Yeah, because if I look at K1, following my nose with this argument that we did for K0, this will be the direct sum of the K1 groups of our matrix algebras. And Rachel proved yesterday that the K1 group of each of these matrix algebras will be 0. So I'm summing up 0 a bunch of times. So this will be trivial. Okay?
For the result in K0, this is interesting because I guess it yields a proof that the number of direct summands in the decomposition is unique for matrices, right?
Yeah, yes.
Because the
Yeah.
K0 group is invariant to the algebra. So there's
Yes.
only like, there has to be exactly n matrices in the decomposition.
Yeah, exactly. Yeah, that's a good observation. I hadn't considered that. Okay. So the nice thing here is that for finite dimensional C-star algebras, we know the K-theory of these. It doesn't matter what specifically the C-star algebra is, we know it's K-theory. So let's do one bump up and think about C-star algebras that are comprised of finite dimensional C-star algebras. So my thought goes to AF algebras, but even more simple than that, let's talk about UHF algebras. Okay, so I know that you talked about these already, but for the sake of completeness, I'm going to redefine what a UHF algebra is, just so that my notation makes sense. I'm not exactly sure what notation Levi used when he gave this talk. So a UHF algebra is isomorphic to, or just is, the inductive limit of the sequence mk1 of C, b1 mk2 C. So I have an inductive limit or a sequence of matrix algebras over the complex numbers. And there's something special about the maps that are going between them. So again, these are in the natural numbers and some unit preserving star homomorphisms, BI. So the unit preserving is important in the definition of a UHF algebra. Okay, so these are AF algebras. We will talk about those right after this one. But again, we know the K theory of the terms in our sequence. So if we want to know the K theory of the limit of this sequence, we hope that K theory plays nicely with these limits and inductive limits. Okay, and that's actually the case as well. And Rordam proves this. It's quite involved. And the statement is involved as well. But let's say that A is isomorphic to, or just is, the inductive limit of the sequence of C-star algebras. I'm not going to state it as just for UHF algebras. This does hold for any inductive limit of a sequence of C-star algebras. We just apply it in nice situations. And so on. Then K star of A, so the K0 group or the K1 group respectively, is isomorphic to the inductive limit of the sequence where we apply the functor to each of our C-star algebras and also the maps. Okay, and this holds for whether I'm considering K0 or K1. Okay. So, like I said, this theorem is in more generality than we need when we're considering a UHF algebra or an AF algebra. These C-star algebras could be anything. But let's do a specific example. My favorite UHF algebra is the car algebra. And this is denoted by m to infinity. And it is the inductive limit of the sequence of matrix algebras with specific maps here that I'll write out. So our sequence here, we start with the complex numbers, and then we go to 2 by 2 matrices over the complex numbers, and then we go to 4 by 4 matrices. You can do 8 by 8, and so on and so forth. But these maps are important. So I'm going to change where I start my index. Instead of starting at 1, I'm going to start at 0 just for the sake of notation here. But let's say I have a complex number. What this map phi naught does is it takes it and it takes that A and it sends it to the 2 by 2 matrix with A's along the diagonal and zeros everywhere else. Likewise, if I have a 2 by 2 matrix big A, this will be sent to the 4 by 4 matrix where we have our block matrix A along the diagonal. Okay, so you can see why this would be a UHF algebra. It's important to know that these B maps preserve the unit. And now we want to compute the K theory. So we'll start with K0 and we'll see what happens with K1 after we do K0. So that theorem by Rordam said what I need to do is I need to apply K0 to this sequence. So let's do that. We know that K0 of the car algebra is isomorphic to the inductive limit of the sequence where I take the sequence above and I apply K0 to it. So let's write that out. So I'm applying K0 to everything. K0 M2 and so on. Okay. So like I said before, we know the K0 groups of the terms in our inductive or in our limit, in our sequence, right? So this is the integers, this is also the integers, this is also the integers, and so on and so forth, right? I have an integer copy in each term. So in order to determine what the inductive limit of this sequence is, I need to know what these maps are doing to our K0 classes, right? So we need to figure out what K0 of phi n does to our K0 classes. Okay, so let's take phi n here and think about what the induced map should be. So what phi n does is it takes a matrix and it sends it to A0, 0, A. Okay, so we know how this induced map on K-theory should be defined. So what I do is we take a K0 class. I'm going to have a little bit of abusive notation. I'm now viewing A as a projection instead of just a matrix. So I'm going to take this class and we apply the to this. Okay, oops, I missed an N. Okay, so what this does is this sends this class to this class here. Okay, we are applying this star homomorphism, Vn, to this matrix A. Okay, and that is exactly what we had before. I now have a diagonal matrix with A's along the diagonal. Great. This looks like addition in K0. So remember, we defined our addition as such. And so this will be taking the class of A plus the class of A. Okay? And so that is giving me 2 times the class of A. Okay, so there are some details that I'm throwing under the rug. There's like matrix amplifications happening, all sorts of stuff. So there's a lot of things that I'm not telling you, and you can fill in the gaps if you so choose, if this is interesting to you. But the idea here is this induced map takes a K0 class and sends it to 2 times that K0 class. So we now know what this map should do to our integers. Because remember, these are the integers disguised as K0 classes, or K0 groups, excuse me. Okay, so what this map does is it takes an integer and it sends it to 2 times that integer. Okay, so now we know what the sequence is. So the sequence that we had before, let me just copy it. Paste. This becomes integers, and then I'm multiplying by 2 for every single map. Okay? So the inductive limit here, remember that's going to be our K0. Oh no, now my pen is mad. Sorry, my pencil disconnected. Why are we having such technical difficulties? Oh my goodness. There we go. Okay, sorry. Wouldn't be a K-theory lecture if we didn't have glitches. So this is isomorphic to the inductive limit of this sequence. And this will be what we call the two addics. There is other notation in different areas of math, but this is what we use. We as in us at CU. I'm not sure if this is standard everywhere else, but what this is this is the group of, oopsies, numbers that look like an integer divided by 2 to some power. So n is an integer and k is greater than or equal to 0. Okay. So I'll leave this up to you to justify this. It takes some getting used to with inductive limits and sequences like this. But for now, let's just believe it. And we now know the K0 group of the car algebra. Okay. So let's think about K1 really quickly. So remember, that theorem that I had before also applies for the functor K1. So K1 also respects inductive limits and the sequence. So this is isomorphic to the inductive limit of the sequence K1. Now I've got K1 again, and you keep going. So similarly to the finite dimensional C-star algebra case, we know that all of these are 0. So I have a sequence of a bunch of zeros. So if I look at the limit, the inductive limit, that's just going to be trivial. So K1 of our car algebra is trivial. And you can fill in the details for that. Justify yourself that that is what we get. Okay. Do we have questions on this?
I'll ask a question. Oh,
Yeah.
Paula can go.
Yeah.
She's a newer student.
You started first, although I don't know if we have the same
Yeah,
question.
you can ask. I probably have a different question.
Well, I was just gonna make a couple of comments. Okay, so yes, I think exercise one, Maggie, and the sort of propositions that you linked 6.5 and boredom. I remember going through that at some point, but yeah, that's got like a nice sequence of these integers. And like the second one of these, like the first one he does is like z to z times one. The next one is times two times three.
Yeah.
And I liked working through that because you see the inductive limit of that is just the rational numbers. And it's
Mhm.
a good stepping stone to see maybe why, when it's all times two times two times two, the inductive limit then gives you this n over 2 to the m or whatever. What did
Yeah.
you call them? I don't know.
The two addicts.
Oh, right, the two addicts.
Yeah,
Yeah, so but
they're like the p addicts.
yeah. And so that kind of made it click for me. And then I guess, okay, yeah, this one for the K1 group, I guess that makes sense. Yeah,
Nice.
nice.
Yeah, I actually had a similar question where instead of the car algebra, I'm guessing you could define like an analogous algebra where it's a limit of a sequence of maps where it embeds the matrix A as like P blocks for some prime P, and then you get the P-adics, I'm
Yes.
guessing.
Yeah,
Yeah,
so
and then I
the
guess the case where you vary the primes
mhm.
over all the primes, it's like you'll end up with the algebra or with the group that localizes by every prime, and that's the same as the rationals. So I
Yeah,
guess that's
so
the idea.
you can do this with like the three addicts. It's just now you're having three uh a diagonal with three entries. So you're doing like 3 to the infinity now. Then you have the three addicts coming up as your K0 group. So yeah, you're right. You can do this for another prime. The car algebra is just the quickest one to do. Okay, great discussions. So let's move on to a little bit more general of a case. So we'll discuss some AF algebras. Okay, so again, I'm sure you've seen this, but I'm going to define it for completion. So an AF algebra is or is isomorphic to the inductive limit of finite dimensional C-star algebras. So more general than a UHF algebra. Okay. So for an example that we can do here for a computation, let's consider the compact operators. It's an exercise in the goals notes, and I'm not sure if Levi talked about it, but the exercise asked whether the compact operators is AF or if it's UHF. So I'll tell you right now that this is AF and not a UHF algebra, but I want to know if you can tell me why. And maybe it'll be clear if I give you the limit of the sequence, because I don't know if that's given in the goals notes, at least at that point. So we have to this, E2, E3. So let's define these maps. So I send this now to A0, 0, 0, A0, 0, 0. So now I'm sending this, instead of having A along the diagonals, I am just putting it in the upper right corner. Sorry, upper left corner, and that's it. So go ahead.
I think Otto has it in the chat, so I don't want to, yeah, but he has it. It's not unital, so.
It's not unital, but also just by our definition, remember that for a UHF algebra, the maps in our inductive, or sorry, in our sequence have to be unit preserving. And these maps here are not unit preserving. So that's another justification as well.
Mhm.
Okay, so it looks like it should be a UHF algebra just because each of the C-star algebras in here is a matrix algebra instead of just a finite dimensional C-star algebra, but those maps aren't unit preserving. Okay, so we can do the same thing that we did last time with the car algebra with this C-star algebra, the compact operators, to find its K-theory groups. It's a little bit more clear what's going on here because these maps are a little bit easier to work with. But let's just take our time here anyway. So we apply K0 to all of our entries. And we also apply it to our maps, but I'm going to be lazy and not write that out. And we already know that each one of these is a copy of the integers. So again, it comes down to figuring out what is going on with these maps. So let's do what we did last time, and let's consider just an arbitrary phi n. So what this does is it takes a K0 class and it sends it to phi n of one of the representatives, and we look at that K0 class. So let's apply phi n to this map. This sends this to A0, 0, 0, and we look at the K0 class of that. So just like last time, this is the direct sum of two projections. And this is how we add our K0 classes. Now, this 0, I'm being a little bit lazy with my notation here. This is the 0 element in our C-star algebra. And Rachel told us that the 0 element in our C-star algebra, that K0 class, will be the identity element in our K0 group, in our abelian group. So this is really and truly just the K0 class of A. So I didn't do anything when I mapped, when I applied this phi n, right? So what this is saying is, oopsies, I forgot my K0. What this is saying is the induced map will be the identity on our K0 groups. M, N, O, C. Okay. So if we are looking at the K0 group of the compact operators, this is isomorphic to the inductive limit of Z with the identity. So I'm not changing anything when I apply these maps. So this is just getting me back the integers, which is exactly what Rachel said yesterday, but this is a different way to go about it. Okay. So again, we care about both K-theory classes, sorry, not classes, K-theory groups. And I'll leave it up to you to justify that the first K-theory group of our compact operators is trivial. It's the same logic that we did for the car algebra. Okay? And this actually holds in more generality as well. So there's a theorem in Roerdam that says if A is an AF algebra, then K1 of A is trivial. So again, I'll let you prove that. It's a fun exercise for inductive limit logic. But that gives us some information about the K-theory of this class of C-star algebras. Okay, so we can say even more about AF algebras and their K-theory. So last time, Rachel mentioned some things about why we should care about K-theory, and specifically one of them is K-theory is used in the classification of C-star algebras. So there's a really nice result for AF algebras and their classification that was proved by Elliott. So let's state that there's going to be some things in here that will not make sense because we haven't talked about them. But I just want to write this out so that we can see that K-theory does have its perks in the classification land. So let's say that A and B are unital AF algebras. These are isomorphic as C-star algebras if and only if the triples, I'll explain a little bit about what these are. Oh, I don't need to write that. 1A, 0. And likewise for B, are isomorphic. So for AF algebras, their K0 groups are very nice. They have very nice structures. They are actually called ordered abelian groups. You may also have heard the term dimension groups before. If you haven't, that's okay. This plus business is what we call the positive cone. It's coming from the ordered structure of our K0 group. And we call the class of the identity the order unit. So what we're saying here is that this AF algebra is not necessarily classified by just its K0 group, but we need a little bit more structure. But this is saying that if we know the K0 group, this positive cone, and this order unit, this comprises the triple. And our AF algebra is completely classified by this triple. So that was a big win for classification. And there's more things going on in the classification world. So if that's interesting to you, maybe look into some other classification things. But now that we have, again, justified the K-theory of the compact operators, we can now discuss the K-theory of the Calkin algebra. So this is, we call it Q of H. I'm going to be lazy and just call it Q. But this is the quotient of the bounded operators by the compact operators. Okay, again, our Hilbert space is the one that I mentioned before. So we have a short exact sequence of C-star algebras, which takes the compact operators, you include it into the bounded operators, and then we do our quotient. So we get the Calkin algebra. So Rachel showed us last time that if we have a short exact sequence of C-star algebras, we get a 6-term exact sequence for K-theory. So, which induces a 6-term exact sequence for K-theory, which we get here. So we'll have K0 of the compact operators, K0 of B of H, K0 of our Calkin algebra, K1 of our compact operators, K1 of B of H, and K1 of the Calkin algebra. Okay. So when we are computing K-theory of a C-star algebra via a 6-term exact sequence, we want to know the K-theory groups of 2 of the C-star algebras that are involved in this, because then we can find the K-theory of the C-star algebra that we are looking for using exactness. And that's exactly the case that we have here. We know the K-theory of the compact operators and of B of H. So let's put those in and look at the sequence that we get. So we know that K0 of the compact operators is the integers, K0 of B of H is 0, K1 of the compact operators is 0, likewise for K1 of B of H. And so we have this. Okay? So by exactness, we have the K-theory of the Calkin algebra that we wanted. Right, so we know that K0 will be trivial and K1 will be a copy of the integers. Okay. So these are some nice examples. I don't have a ton of time left, so I don't want to get too far into the next examples that I have. But other examples that are good to look at would be C0 of X for specific spaces X. So what I'm thinking here is if I have like a compact Hausdorff space that's contractible, that's a very nice example to go through. You can also do this for 0, 1, likewise the real numbers. You can consider this for half open intervals as well. So there are a ton of exercises in Rordom that go through these. So I might list them out and list out the examples if you're interested in this, just because we know a lot of C-star algebras look like this sort of space. Okay, so I think with that, I am going to stop here because some of these take a little longer than I wish to give it, giving the time constraints. So I'm going to stop the recording and open for questions.